Okay, what does this mean? Let's recall that metabolic rate is a flow rate of energy. That is, it's an indicator of metabolic power with units of watts. What are the evolutionary implications of this? In general, animals use energy for three purposes: homeostasis, that is maintenance of the body's integrity; growth, that is increasing the mass of highly organized matter, that is the organism; and reproduction. Energy devoted to either homeostasis or growth is processed internally to the organism. Energy devoted to reproduction, in contrast, is directed to producing new organisms. This is our important evolutionary implication because in our standard evolutionary model, reproduction is equivalent to evolutionary fitness. More energy diverted to reproduction therefore means higher fitness. It stands to reason, then, that any adaptation which increases the metabolic power diverted to reproduction will increase the evolutionary fitness of the lineage and will be selected for. So let's ask an interesting question. Can we derive a thermodynamics of evolutionary fitness? Here's how it might be possible. Let's start with an electrical analogy. There's a simple formula that lets us calculate power from the product of the voltage V and the current I. We can write a similar equation for the metabolic rate. Metabolic rate is equivalent to power. After all, both have units of watts. Here, the voltage term is equivalent to the redox potential gradient that drives electrons from glucose to the ultimate electron acceptor. And the current is, well, the current, that is, the rate of flow of electrons from bonds in glucose to the ultimate electron acceptor. There's a fun trick we can do with the equation for electrical power. Ohm's law lets us express the current as the ratio of the voltage over the electrical resistance. Therefore, the equation for electrical power becomes the ratio of the square of the voltage over the resistance. We should be able to do the same thing for our equation for metabolic power. This now allows us to ask our interesting question in a more precise way. An animal seeking to increase its metabolic power has two options for doing so. It can increase the rate of flow of electrons through its body, that is the current. This means basically increasing the rate of consumption of fuel molecules like glucose. Or it can shop around for electron acceptors that increase the redox potential gradient driving the flow of electrons. A clear advantage accrues to the latter strategy. To see why, let's look at those redox potentials again. The redox potential that drives electrons through glycolysis, that is, fermentation, is on the order of about 0.3 volts. The redox potential that drives electrons through oxidative phosphorylation, that is, respiration, is about 4 times greater, about 1.2 volts. The power advantage that accrues to using oxidative phosphorylation rather than glycolysis is not 1.2 over 0.3 or 4, though, but the square of the ratio, that is 16. This is why the ATP yield from oxidative phosphorylation is about 16 times greater than the ATP yield from fermentation. So, by using electron acceptors that magnify the redox potential gradient, animals can get much more bang for the buck, so to speak. This is why oxygen is so important. Oxygen is the most electronegative of all the elements, and that means there is no element that can beat oxygen for maximizing the redox potential for driving metabolism. And this is why selection has tended to favor metabolic systems that employ oxygen as the final electron acceptor, despite the fact that oxygen is so toxic and so dangerous. There are interesting stories that follow from this. One is focused at the tiniest scale imaginable, but has profound implications for health and disease. And the other is an epic story of the evolution of life itself.